All right, Algebra 2. Let's move on into section 5.2, which is kind of a long section right here, so I'm probably going to break this one up into two videos. In section 5.2, we build on what we learned in 5.1, where we kind of talked about what a monomial was, what a polynomial was, and we talked about end behavior quite a bit too. Now we start going a little bit further into our understanding of polynomials, with the end result right here of being a little bit better at graphing them with a little more accuracy by the end of this section than we were able to do at the end of 5.1. So, unfortunately, this first slide is pretty long here, guys. We got a lot of vocab that we've got to hit, but we're going to be talking more about polynomials today and a discussion of linear factors, and then this word right here, zeros, which we haven't really defined yet for you guys, so we're going to work on that. All right, into part one right here, guys. We're going to start talking about the connection between a few different terms right here that are really going to be used almost interchangeably: roots, zeros, and x-intercepts. Those are three things we're going to be talking about here. So what we have right here, everybody, is something that we wrote down in our 5.1 notes. This is standard form of a polynomial function. Polynomial, which is why we're calling it p, and x is our variable. So p of x is equal to, and this is what standard form looks like. A is your leading coefficient, x is your variable, and we take it to a power that's going to be n, which has to be a positive integer. And then with each subsequent term, we have a new coefficient that isn't really related to anything in the previous term, the same base of your exponent, your variable, which is x, and the exponent drops by 1 compared to what it was before. And then we keep going. We have a third term with a new coefficient, the same x, the same variable as the base of your exponent, and your exponent drops by 1 yet again. And then you can keep doing this as long as you need to, but we end with this k value here, which has no x and has no exponent on it. That k is your constant. So that is standard form of a polynomial function. And when you write a polynomial function like that in standard form, this is where it becomes important right now, guys. All of the following statements here are equivalent. You can only see two here, but I'm going to scroll up in a minute. There are actually four. So here we go. The first thing: the binomial quantity x minus q is a linear factor of the polynomial function p of x. Well, the p of x is in reference to what we just wrote down right here, but where'd the q come from? That's something that's totally new right now, guys, and we're going to talk about how to factor a higher order polynomial than what we dealt with back in the middle of chapter 4, but we'll get to that later. So once you do that factoring, this number here, q, which is being subtracted from x, if that's one of your factors, then the next three things kind of have to be true. So it wouldn't be a terrible idea to put a word if right here, and then we can pick up with then on statements 2 and 3 and 4. So if x minus q happens to be a linear factor of p of x, then here's the first conclusion. That number q that we just talked about is what we call a zero of your polynomial function. So again, that's a new phrase I don't think you guys have heard in Algebra 1. You certainly didn't hear it in geometry, and I doubt we used it yet this year in Algebra 2. But a zero of the function, everybody, does this statement right here. You'll notice that q is in the place of the x right over here, guys. Q is an x value that you can put into your function p and get a y value equal to 0. All right, so q is an x value that makes y equal 0. That's the important thing to understand about what a 0 is. Okay, and now if we have that, then I tell you what, guys. Oh, I didn't want to do that. All right, let me scroll out a little bit here. Let me draw a little line, and that'll let me do this. Okay, gotcha. The third thing we want to talk about right here is that q itself, just the number right there, is called a root of the polynomial equation. And we usually just use the word solution to an equation a little bit better, but basically then, if q is a zero of the function, which we wrote back here in part 2, then we can also say that q is a solution to this equation right here. P of x equals, but it's got to be 0, everybody. If this was a number like 5 instead, you'd want to subtract that 5 over on the other side to get it equal equal to 0. So it's pretty much the same thing to say that q is a 0 of a polynomial as it is to say that it is a root or a solution to that equation p of x is equal to 0. And the fourth thing we wanted to talk about, the one we're actually going to spend a lot of time talking about today, is a graphical interpretation of that. If q is a 0 of your polynomial or a solution to that polynomial equation, then you can also say that q is an x-intercept of the graph y equals p of x. And we all do a better job, guys, processing information that comes to us graphically. So this graphical interpretation of a linear factor or a 0 or a root is probably going to be the easiest one for us to understand because we have been talking about x-intercepts all year long. An x-intercept, if you remember, guys, let's talk about maybe, how about just a line right here, a linear function. Its x-intercept is where that function crosses the x-axis. So that one point that I just made right there would be the one x-intercept. Or if it were a quadratic function, a parabola that opens upward like this function would have two x-intercepts, which means it has two x-intercepts, two roots, two zeros. All those phrases go hand in hand. Okay, so with that in mind, guys, let's see what we can move on to here in slide 2, where we're being asked to find the zeros of this polynomial function, which was given to us, and we're going to come up with a rough sketch of the graph of this thing. And what I want everybody to realize here is that this polynomial function, p of x, is not really written in the format of this polynomial function right here. This one, the way it was written out, is in what we would call standard form, and hopefully you have that in your notes from section 5.1. But in problem number 2, what we're looking at right here has already been put for you into factored form. Now that's something we're going to have to learn to do for ourselves later on in chapter 5, but for our very first problem, we gave you one that was already factored. Okay, so we're supposed to find all the zeros of this polynomial, and if I go back to that list we wrote a second ago, q is a 0 of your polynomial if, look right here guys, if p of q is equal to 0. So we're going to take that polynomial function here in number 2, and we're going to set it equal to 0, and we're going to try to solve this. Now, solving a polynomial equation like this can be difficult, but again, this one was already given to you in factored form. And you guys learned something in the last chapter called the zero product property. It's not something people usually know by name very well. Even my calculus students, if I asked them what it was, they wouldn't know. But the zero product property says that, what do we got here, guys? That if you have got a factored expression like a times b, that will equal 0 if either a is equal to 0, the first factor, or if b is equal to 0, that would be the second factor. Well, it actually works, guys, no matter how many factors you have, because multiplication by a 0, no matter how many numbers you're multiplying it by, will always get you 0. So if I crammed in a third factor here like times c, then I could just keep going here. A times b times c would equal 0 if either a was 0, or b was 0, or if c were equal to 0, there'd be kind of a third solution from that equation as well. So back to this problem, you've got a 3-factor expression here set equal to 0. So all we do is set each one of those 3 factors, start off with x plus 5, equal to 0, and solve that one. And here we're just subtracting 5 from both sides, and we'll get x equals negative 5. Here, we'll set the second factor, x plus 1 equal to 0, and we'll get x equals negative 1. And our third factor, x minus 3, we'll set that equal to 0, and we'll get x equals 3. So these are the 3 zeros of this polynomial right here. So it's not a bad idea to put the word or in between each of those. So those numbers right there are the zeros that we were asked to find here in that polynomial. It had 3 factors, so therefore it has 3 zeros, 3 values of x that if you put them into this function, you'd end up with 0 for the value of the entire thing. Now, what sounds difficult is that they're also asking us to graph this function, but this graph really isn't that bad if you understand a few things here about polynomial functions. We just found 3 spots here, guys, 3 values of x that would make your y coordinate equal 0. And if I go back to this long explanation right here we had on the first slide, take a look at the 4th thing that we have right. Actually, let's look at 2 and 4. Number 2 tells us right here that we are dealing with a 0 of your polynomial function. And then if we jump down to number 4 right here, now we're saying that that same number, q, would have to be an x-intercept of your graph. So the 3 zeros that we just found here in problem number 2 here in these notes, guys, those are the x-intercepts on your graph. So we've got one of them right out here. I'm just eyeballing this graph right here, guys, at -5. We have another one right over here maybe at -1, and another one over here to the right at x is equal to 3. So what we've learned from the first part of this problem is that this polynomial function crosses the x-axis 3 times because it has 3 zeros, once at -5, once at -1, and once at 3. Okay, well, we've got 3 points on the graph right here. Whoopity-doo, does that really tell us what the graph looks like? By itself, not that much. But if you remember thinking about end behavior yesterday, or I should say in the previous section in 5.1, that can help you out as well. So let's think about that, and hopefully this is going to be something that you're able to do mentally before we get too far, but for now, we'll write it out. As x approaches positive infinity, the value of our function, p of x, approaches, well, let's think about this. We're letting x be a large positive number. So let's put it right up here. A positive number plus 5, that's going to be positive. A positive number plus 1, that's going to be positive. And a positive number minus 3, assuming that it's a large positive number, that is going to be positive as well. And we're multiplying positive times positive times positive. That result is going to be positive also. That means our y value will approach positive infinity, and this function goes up on the right. Let's keep that in mind. And then the second end behavior is what happens as x approaches negative infinity. So let me erase those plus signs that I put right there. Now, what happens if we let x be a large negative number? A big negative number plus 5 will be negative. Another big negative number plus 1 will be negative. And any negative number minus 3 will be negative as well. Negative times negative times negative is going to be negative. So that tells us that as x approaches negative infinity, p of x, which will be negative, approaches negative infinity as well. This function goes down on the left. Now, given that my polynomial graph has to pass the x-axis at these 3 points, here, here, and here, and given that it goes up on the right and down on the left, I actually do, right now, have a pretty good sense for what this polynomial function looks like. It goes down on the left, and that -5 is its first x-intercept. Then, in between -5 and -1, it's got to come up above the x-axis, but then come back down to hit the x-axis again at -1. Then it's going to dip below the x-axis between -1 and 3 before coming back up. And then paying attention to my end behavior at the end, it's going to increase at an increasing rate here. And that, everybody, is a pretty decent guess for what the graph of this function looks like. I've got the 3 zeros, or the 3 x-intercepts, right. I've got the end behavior right on the left and the right, and so that's as accurate as we're going to ask you guys to be until we get to something new at the end of this section. Now, I'd hate for you guys just to take my word for it there, so what you guys would probably do is grab your calculator, press your y equals button in the upper left-hand corner, type in this original function just the way it's expressed right here, and then hit the graph button in the upper right-hand corner to see what that looks like. Now, I took the time on my calculator here, which is different than yours. Sorry, guys. But I took the time to define some of these functions. So if you look there, that first line that I have, f1 of x, that is the function we are dealing with right here. Although, hang on a second. I think I goofed it up. I think that was supposed to be an x plus 5, wasn't it? Yep, I just caught that before I did it. So let me go back here. Let me see if I can, let's see, copy that and then put this down here. Will that paste? Okay, and I just need to change that x minus 5, sorry everybody, into an x plus 5. That would have been bad. All right, let me hit enter. And now, let's see if we can get this thing to actually graph. So I want to go up and I want this thing to graph my f1 of x function, which I've already defined. Here it is. And if I hit enter, and then get this key, oh, that didn't work, and then get this keyboard out of the way, that should have done what I wanted it to do. Okay, there we go. So, can't see everything you wanted to see here, so I'm going to pinch zoom out of this thing and see if we can see a little bit more. All right, the graph is maybe a little weirder than you expected it to look, but that's what's going on here, guys. If you take a close look at this graph here, oh, I keep messing with it, sorry, it is going down on the left and up on the right, and it looks like it's crossing the x-axis at the spots that we talked about right there, which are at -5, and then -1, and also again at +3. So, yeah, roughly, that shows us about what we wanted to see at that point there. Okay, so that's how you can use the zeros of a polynomial function in order to come up with a rough sketch of its graph. Okay, on to something different now. Here in this section, they're also going to ask you guys to take a function where they gave you its zeros. Here we have 3 of them, and we're supposed to write a polynomial function. So we're kind of doing the exact opposite here of what we did in problem number 2. In this problem, I gave you the function, and I asked you to come up with the zeros. That's the work that we did. Now it's the other way around. We have the zeros. They're asking us to write the polynomial function. So, using what we've talked about here, guys, each one of those zeros correlates to a linear factor of p of x. And the first factor here is going to be x minus this particular number right here, but it's always minus, guys, so it's going to be x minus 3 for our first linear factor of p of x. If you think about that, the reason that works is because if you put that 3 in here for x, 3 minus 3 would get you 0, and that's exactly what we're looking for. 3 is a value of x that would make the function become 0. So there's x minus 3, got it. The second factor is going to come right here. It's x, and you always want to think minus whatever this number here is. Minus -1 would just be more easily written as +1. And the last 0 is +4, so we're going to do x minus this number right here. And there's your polynomial function in, let's write it out everybody, this is in factored form. Unfortunately, the directions tell us we're supposed to write our polynomial function in standard form. So what do we get to do now, guys? We get to multiply this out. And I think this is going to be the first time this year that we have FOILed out 3 different binomials together. So here's the way I'm going to do this, guys. This is a 3-part multiplication problem. My preference, I'll explain why in a minute, I like to multiply the second and the third parts together first, then come back and deal with the first one after that, although you don't have to do it this way. So I'm going to leave the x minus 3 here, and now we're multiplying x plus 1 times x minus 4, binomial times binomial. This is where we're going to do FOIL. So I'm starting a set of parentheses, and here we go. First product, x times x, is x squared. The outer product there, I'm going to try to do this mentally, guys, is -4x. The inner product is plus 1x. So negative 4x plus 1x is going to be a negative 3x. And then the last product is this positive 1 times this negative 4. That gets us a minus 4 at the end. So we FOILed out the second and the third binomials. Now, we have to multiply the x minus 3 into this. And as I said, I don't think we've done this yet this year, multiplying a binomial into a trinomial. So here's the way we're going to do this, guys. Double distributive property. We start with the x right here, and I like to take that x and distribute it into this trinomial, and I'm going to write the results right here. X times x squared is going to get us x cubed. X times minus 3x is a minus 3x squared, and then that same x times a negative 4 is going to be a negative 4x. And we're halfway home, everybody. I'm going to switch colors to green now. Now I'm going to take the second term in this binomial, which isn't 3, it's negative 3, and I'm going to distribute that negative 3 into the trinomial as well, but I draw that on the bottom just to kind of keep things clear. Now, negative 3 times x squared is negative 3x squared. But I'm not going to write that here, you guys. Instead, I'm going to write it right there. I'm trying to get my like terms to line up because I think it's easier then to do our next step. So negative 3 times x squared was negative 3x squared. Negative 3 times negative 3x is going to be a positive 9x, and you'll notice I wrote that under the x term. And then negative 3 times negative 4 is going to be a positive 12. There was no constant in red, so there's nothing really to write that underneath. It kind of hangs out there by itself. And so now, guys, I think I can just barely cram our final answer in here. We have to combine like terms. There's nothing to combine with the x cubed, so that's just it. X cubed minus 3x squared is a minus 6x squared. Negative 4x plus 9x is a plus 5x, and that plus 12 just goes along for the ride. So that right there, guys, is going to be our answer here, doing what they asked us to do, writing a polynomial function in standard form with those following zeros. Okay, so that's our answer for number 3, but again, I want to show you guys that this actually worked out the way that we wanted it to. So let me go back over here. Let me turn off graph F1, but I think I have defined F2. That right there should be the answer to the function that we just came up with. And yeah, I think I've got that right. So if I turn that one on, let me do that and hit enter. There you go. That is the graph of the function that we were just dealing with. And what do you see here, guys? We knew at the beginning of that problem that we had zeros at 3, negative 1, and positive 4. Zeros are the same as x-intercepts. And so if you take a look at where this function here, that curve, crosses the x-axis, yeah, it looks like it crosses the x-axis once at negative 1. That'd be the point furthest to the left. Then if you move to the right, it crosses at 3, and it crosses at 4 as well. So I feel pretty confident then about what that graph looks like. Okay, so that was 3A. Want to do one more with you here. It gets harder. Now, what I'm hoping you may have noticed from both of the last two problems, let me go back 2 here. In example 2, I gave you a function that had 3 factors, and it ended up being, wait for it, oh, you can't really see that here, a cubic function. This example shows the exact same thing. There were 3 zeros right there, and a function with 3 zeros is going to be a cubic polynomial. And sure enough, we saw that right down here, guys, that we ended up with an x to the 3rd in our final answer. It was a cubic polynomial. So what are we expecting to happen here? Now that we've got 4 zeros, okay, I'm hoping you guys can come up with this conclusion on your own. We are going to end up with what is called a quartic polynomial, which means we're taking x to the 4th power in our final answer. All right, let's see what this one's going to look like. Same basic concept. P of x equals, and here we go. It's always x minus each one of those zeros. So x minus 2, and then x minus negative 2 becomes a plus 2. X minus 5, got it? And then an x minus 3. So that's what P of x would look like in factored form, but we need it in standard form. And now with 4 polynomials, I'm going to go ahead and FOIL these 2 together here and these 2 together here at the exact same time. So let's see where this gets us. P of x equals, and here we go. Now I'm hoping you guys recognized this binomial is the conjugate of this binomial right here. So something cool happens when we FOIL that. X times x is going to be x squared. The outer product here is plus 2x. The inner product would be minus 2x. They cancel each other out completely. And then the negative 2 times the positive 2 is going to get us a minus 4. So foiling the first 2 binomials together, we end up with another binomial, that's unusual, of x squared minus 4. I don't think we're going to get that lucky here. X minus 5 and x minus 3 are not conjugates, so I think we're going to end up with a normal trinomial. First product, x times x, is x squared. My outer product is a negative 3x. My inner product is a negative 5x. Those combine to make a negative 8x. And my last product, negative 5 times negative 3, is a plus 15. Can't simplify that any further. And now, you guys, this becomes a problem just like what we had in the last one. We're distributing now, or double distributing, I should say, a binomial into a trinomial. So I start with the x squared. Let's see where that gets us. X squared times x squared is x to the 4th. X squared times a minus 8x is minus 8x cubed. And an x squared times 15 is a plus 15x squared. Done with that part, let's switch to green now. And now we're going to distribute this negative 4 just on the bottom side. Negative 4 times x squared is negative 4x squared. And I'm going to write that under the x squared term that's already there. Now I think I'm in no man's land. Negative 4 times negative 8x is a plus 32x, and a negative 4 times a positive 15 is going to be a negative 60. Okay, I think that's as much as we can do right there, so let's write it all out now, and this should be our final answer. P of x equals, and it looks like we've got an x to the fourth, a minus 8x cubed, and how boring is this? The only combining of like terms I get to do is right here. 15x squared minus 4x squared is a plus 11x squared, and then the plus 32x and the minus 60 just come down, and that should be our answer here, everybody, for the polynomial function, the simplest polynomial function in standard form that has these 4 zeros. So let's check that one on the calculator too and see how I did there. So let's see, I'm going to go up and turn off the graph of f2 of x, no thank you, and then I'm going to go down to the graph of f3 and try to turn that one on, and it seems like if I just fix that number right there, there you go. All right, guys, so this function, a little bit different than some of the ones that we've dealt with before. Boy, it's kind of a really skinny W. That's kind of what I see here. But most importantly, let's look close right here, guys. We wanted to know when this thing, or where this thing, crosses the x-axis. It looks like it crosses it at negative 2 here on the left, somewhere around where I just clicked. Let's see. Then over at positive 2. Looks like positive 3 and positive 5. So I think those are the zeros that we had right there. Negative 2, positive 3, and positive 5. So that graph kind of verifies that we're doing this one correctly. All right, guys, let's keep going with it right here. Next thing we're going to talk about is a concept called multiplicity of zeros. Now, in that previous problem, in fact, in the previous 2 problems, I told you guys that every single time you have a 0, your function crosses the x-axis, and I probably should have used a different word. Every time it has a 0, it touches the x-axis, but it doesn't necessarily cross it. So let's talk about this concept. Multiplicity of zeros refers to the number of times that a 0, or remember guys, a linear factor, occurs in a polynomial. In the problems that we've done so far, each 0 has only occurred one time. But let's go back to this last one. If I changed, just for example, this 3 into a 5 again, now you'll notice the 5 occurs twice. Now this function still has 4 zeros, but that's going to alter some things about the graph itself, and that's what we're going to explore right now. So the number of times that a 0 occurs is its multiplicity. And here's a couple rules we need to know, but you'll get the hang of them pretty quick. If that multiplicity is odd, meaning 1 time or 3 times or 5 times, that means that your graph, and I want to underline this word right here, crosses the x-axis at that 0. But if your multiplicity is even, if it occurs twice or 4 times or 6 times, then we would say that your graph bounces off the x-axis at that 0. So maybe just a real quick graph of what a picture of what I'm talking about right here. If you had an odd multiplicity, your graph would cross through the x-axis. So it would look something like this right here. But if you had an even multiplicity, what would happen then, guys, is that your graph would hit the x-axis, but then bounce off it and go right back from whence it came. So this is what it looks like when you have an odd multiplicity. It goes through or across the x-axis. This is what it looks like when you have an even multiplicity. It hits it, but then goes right back in the other direction there. So let's see that in action. So we're going to find the multiplicity for each one of the zeros of this function, and then we're going to come up with a graph of this. Not a super accurate graph, but a relatively rough one. And again, we started off with a nice one here, guys, that is given to you in factored form. It'll be harder. I think on the very next example, you're going to have to do some factoring on your own. But we started you off with an easy one right here. So here we go, guys. The first factor here is x. And for some reason, I get it, people know what to do with this and with this. They don't know what to do with this one, which is actually much, much easier. You just take each factor, our first factor is x, set it equal to 0, and solve. Well, that one is already solved, you guys. What value of x will make x become 0? 0. There's your first solution, your first 0 right here. And now, what's the multiplicity of that 0? How many times does this x occur in the factored form of this polynomial expression? Just once. There's only one x all by itself there. Okay, our second 0 comes from our second factor. So we take x plus 2, set it equal to 0, and solve. We'll subtract the 2 on both sides and get x equals -2. So that is our second 0. And how many times does that occur? Just once as well. But the third 0 is going to come from this one right here, which you'll notice is squared. So technically, I should set x minus 1, quantity squared, equal to 0, and solve from there. Well, as I think you're going to figure out pretty quickly here, guys, you end up with just x equals +1. But its multiplicity is actually a 2 here, and it's because that x minus 1 occurs twice. You could have, if you wanted, not put the 2 right there and just written another factor of x minus 1, and now you can see we've got a 0 of 1 and a 0 of 1 again. But however you slice it, we end up with 2 for our multiplicity. Actually, let me undo a lot of what I did there. I just made that ugly. All right, and there's a 2. Okay, so that's what this little table looks like. We have 3 zeros, but one of them has a multiplicity of 2. All right, so now we're supposed to come up with a graph for what this function looks like. So let's see what we know here, guys. Boom, ba-boom, ba-boom, ba-boom. And, okay, I didn't make this that big and scary here. I don't have to make my graph very big. This function here, let's take a look, touches the x-axis at 0. That was our first 0. That's a little misleading. -2, that was our second 0. And also at +1, I didn't draw that very well, but it looks something like that. Okay? Now, let's talk about end behavior real quick. As x approaches positive infinity, let's think about what y does. This number will be positive, this number will be positive, and this number will be positive squared. So this is positive times positive times positive. That means that y, or f of x, is positive. It's approaching positive infinity as well. So this graph goes up on the right. As x approaches negative infinity, this is a little bit harder. Let's think about what happens when we put negative values in here for x. This first factor here is going to be negative. Then a negative number, a huge negative number, plus 2, that'll be negative as well. So this is negative times negative. And now over here, a negative number minus 1 will be negative, but then you're going to turn around and square that negative number, which is going to make it positive. So we are talking about the product here of a negative times a positive, which is going to be positive as well. F of x still approaches positive infinity, so this graph goes up on the left as well. Now, so far, I'm just approaching this problem the way we did some of the first examples in our graphs, or this section of notes. So I'm pretty sure that this graph is going to go up here on the left. But if I do this one, you should probably stop writing right now, guys. I'm going to do something wrong here. If I just do this the way that I did before, I would have it come down and then come back up to hit the next 0, then go above the x-axis and then down, but it never turns back up. And I thought I knew from my end behavior that the function was supposed to go up on the right, but I either have it going down on the right, which contradicts that end behavior, or to do that, I would have to turn it and make it go back up, but now I just introduced another 0 that we didn't find when we looked at the function analytically. So something's got to give right here. The way that we've been talking about this problem up until now doesn't really seem to fit things that we know. Well, that's where multiplicity comes into play. So let's take a look here, guys. Our first 0 right here is -2, where we had a multiplicity of 1. And what did we write down on the previous slide? If your multiplicity is odd, then your graph crosses through the x-axis at that point. So I think I was right in bringing this graph down like this. Our next 0 is going to occur at 0 right here, where again we have a multiplicity of 1. And that means once again that this graph crosses through the x-axis at x equals 0. So yeah, I was right about that too. It's going to come above the graph like this. But our next 0 looming is at x equals 1, where our multiplicity was 2. And what did we say right here, guys? If your multiplicity is even, like 2, your graph bounces off the x-axis, but it doesn't actually cross through it. it. So at this spot here when x is equal to 1, I need to draw a function that hits the x-axis but then bounces off of it and moves back up then as we move to the right. And this graph, everybody, this W shape, kind of supports what we thought we knew here about our end behavior. This graph goes up on both sides. So that is how multiplicity of zeros is kind of interesting. This is actually, you'll see on the next problem, this is actually a fourth degree function, everybody. It is quartic. The way I knew that real quick is because here I have an x squared times x times x. So that's x times x times xx. There's 4. You would expect that a quartic function would cross the x-axis 4 times. This one only crosses it 3 times. And it's because of multiplicity that those two things might not exactly match up. Okay, the last problem I'm going to do on this video with you guys here is just another variation on that one, but you'll notice, unlike the previous problem, this one is in standard form. We need to get it in factored form, you guys, in order to figure some things out about its multiplicity. So this is going to take us back into some work that we were doing in the middle of chapter 4, factoring polynomials. And in fact, that's a big focus of what we're going to be doing in the rest of chapter 5. For now, this one is just a very small step beyond what we did in chapter 4. What you guys were taught, and hopefully you learned, is that the very first thing you want to look for in any factoring problem is a greatest common factor. And if you have one, you want to use what is really the reverse distributive property to pull that GCF out in front. So if we look at all three of these terms, here and here and here, there's no number other than 1 that divides into 1 and 2 and 15. So you can forget about that, but we can pull out variables here. Those three terms have 4x's, 3x's, and 2x's. That means that we can pull out 2 of them. So I'm going to bring out an x squared. The other thing I'm going to do, nobody likes having a negative number right out here in front, or I should say a negative leading term. So I am also going to pull out that negative along with it. So that's the GCF that I'm going to pull out. What's left? Negative x to the 4th divided by negative x squared is going to give us a positive x squared. Then the second term right here divided by our GCF, because we pulled out a negative, that plus 2 becomes negative 2. There were 3 x's there. We've pulled out 2 of them, so there's just 1 x left. And lastly, the 15x squared, we're dividing out a negative, so it's now minus 15. And hey, there were 2 x's. We pulled both of them out. There are no x's left. And that is what this expression looks like after we have factored out a GCF of negative x squared. And guys, that negative x squared, that GCF, doesn't go away. It stays there on my next step. In some cases, you might be done, but not here, guys. We're left with, hopefully you know the name here, a quadratic trinomial. And hopefully you recognize that because we saw a ton of those in chapter 4. So we're going to try to factor that one with reverse FOIL. And everybody's got their own method for doing this. However you're comfortable with it, go right ahead. For me, what breaks up into x squared? Well, that's going to be x times x. I would read my signs here, and that minus tells me that these two signs are going to be different. 1 plus and 1 minus. And I'm looking now for two numbers that multiply to negative 15 and add up to negative 2. Okay, 5 and 3 are what I'm looking for here. It's going to be a minus 5 and a positive 3. So however you get to that spot, great, you're good to go. And now we've got it fully factored. So now you would set that polynomial function equal to 0 and try to come up with your zeros. All right, guys, looking at the first one, let me make this nice and easy for you guys. Anytime you pull out a monomial, like in this case, negative x squared, what value of x would make this thing equal 0? The answer to that is going to be 0. But the multiplicity there comes from the exponent of 2, so that 0 has a multiplicity of 2. I've got a 0 that comes from right here. Setting x plus 3 equal to 0 would get me x equals negative 3. And because there is no exponent up there, we know that's really an exponent of 1. So that would be our multiplicity of 1 for that 0 of negative 3. And lastly, what value of x would make x minus 5 equal 0? 5 would be our last zero here, and again, just a multiplicity of 1. So trying to come up with a quick sketch of the graph here, guys, let's see what we've got. I've got zeros at -3 and +5, 3, 4, 5, okay, and at 0. So let's start plotting those points right there. A 0 at 0, got it. A 0 at -3, got it. And a 0 at 5. Got it. Now, if I think about end behavior, everybody, as x approaches infinity, the value of this function, g of x, would approach, well, let's find out. A positive number to the 4th power is positive, but then you got to take the opposite of that right there. Actually, you know what? I'm looking in the wrong spot. We should focus right here on the factored form. Let's try that again. A positive number squared is positive, but the opposite of that is going to give you a negative result. Positive infinity plus 3, yeah, that would be positive, and a huge positive number minus 5 would be positive as well. Negative times positive would be negative. G of x is approaching negative infinity. We are going down on the right. Now, the other end behavior, as x approaches negative infinity, we're looking to the left. What can we figure out about g of x then? So let me erase some of these marks that I made here, and let's think about putting a negative number in for x. A negative number squared is positive, but the opposite of that will still be negative. A big negative number plus 3, negative, and a big negative number minus 5, negative. So negative times negative times negative is negative. We're approaching negative infinity on the left as well. So this graph looks like it's going down on both sides, which by this point, I'm hoping you guys are getting a sense for this. A negative 4th degree function, yeah, is going to go down on both sides. So here's what I know, guys. Starting at my first zero of -3, I know this graph is going to go down as I look at it from right to left, looking like that. But at -3, my multiplicity was 1, which is odd. So that means that this graph goes through the x-axis and is going to turn around right here to hit my next zero at 0. But at that spot, our multiplicity is 2, which is even. So it's not going to cross through the graph like that, everybody. It's going to bounce off the graph and look something like that and go back up into the first quadrant. And then we're going to turn direction at some point here and approach our last zero of 5, where our multiplicity is 1, which is odd. So it will cross through the x-axis then, and then continue heading downward like that. So I end up with this kind of McDonald's M-looking shape here, guys, and that's what we came up with for this graph. So multiplicity gives you a little bit more information about what the pictures of these graphs are going to look like. I've got just a couple of slides left, but I think I'm going to go ahead and wrap up this video and then make a part 2 after that. So good luck with everybody, what you're working on 5.2, and then check out that second video to talk real quick about max and min values.